Okay, so one thing we can do besides the sequence of partial sums is to look at whether or not the sequence has some particular properties to it. So one of the most common series you're going to come across, even outside this class, if you ever have to deal with series, is typically something called a geometric series. Now, a geometric series is a series that has this form to it. The sum as n goes from 0 to infinity of a r to the n. Okay? Where a is something that's just going to be a constant. Okay? R will also be a constant we're going to call the ratio of the series, and n is your index. That's the thing that's going to be changing. So the first term would be ar to the 0, which would just be a. The second term would be ar to the first, then ar to the second, all the way up to ar to the n, and it'll keep going. A can't be 0, because if a was 0, then every single one of these terms here would just be 0. So we're not going to look at that. But if a series has that structure to it, we call it a geometric series. Whether or not that geometric series converges or diverges has everything to do with the ratio of the series. Okay? So this is what geometric series theorem says. So a geometric series with ratio r diverges if the absolute value of r is less than or equal to 1. And if the absolute value of r, greater than or equal to 1, did I say less than? Yeah. If the absolute value of r is greater than or equal to 1, it diverges. And if the absolute value of r is less than 1, the series converges. Not only that, the series itself converges to, or is equal to, a over 1 minus r. So this gives us two things: converge or diverge, and what it converges to. And the only thing that we need to look at is r. So when you look at a series like this or like this, if you can recognize that these are geometric series and you can identify what r is, then you can determine whether or not these series converge or diverge without having to go into the partial sum concept at all. Now there's a reason why the theorem says what it says, and we'll look at that in a second, but let's just look at these two examples. So the first one, A. If we look at this sum, and I rewrite it as n equals 0 to infinity of 3 times 1/2 to the n. That's the same thing as this. Because if I raise 1 to the n, I would get 1. If I raise 2 to the n, I would get 2 to the n. So this is the same thing as 3 times 1 to the n over 2 to the n with the sum. Okay? And 1 to the n is just 1, so again, this is the same thing. All right, let's erase all this business here. So if I look at it as this, well, that has the form of the sum of a r to the n, where r is 1/2. So this is a geometric series with a common ratio of 1/2. So that ratio of 1/2 is going to tell us whether the series converges or diverges. So I look at the absolute value of 1/2, absolute value of r. Well, that's clearly less than 1. Since the absolute value of r is less than 1, the geometric series will converge. Okay? That's it. If this is a test question, you gave me everything I needed. You said, all right, what type of series is it? It's geometric. What happens to it? It converges. And why? Because the absolute value of 1/2 is less than 1. Now, there's another part to this. Since it converges, can you also tell me what it converges to? Well, yeah, you could say the series converges to a, which is 3, over 1 minus r, which is 1/2. Well, that's 3 over 1/2, which is 6. So this series, if I added all the terms together, would add up to 6. So it converges and it converges to 6. That's everything you would need here. Now, one thing to note, that the series has to start at 0 for it to converge to a over 1 minus r. But the series doesn't have to start at 0 to be a geometric series. If I look at the series n equals 1 to infinity of 3 over 2 to the n, that series compared to this one is still a geometric series because it has everything a geometric series needs to have. It just doesn't start at 0, it starts at 1. So this is a geometric series. It's still going to converge because the absolute value of r is less than 1, but it doesn't converge to 6. Because if you look at this series and you start looking at the first couple terms of this series, which would be if n equals 1, you would get 3 halves. If n equals 2, you would get 3 over 4, then 3 over 8, then 3 over 16, etc. And you added all that up versus this series, which is 3 over 2 to the n, where n starts at 0, this would be 3 plus 3 halves plus 3 fourths plus 3 eighths plus 3 sixteenths. And I know when I add all that up, it's going to add up to 6. But if you look at these terms versus these terms, this is the big difference. This one's got an extra term in the front that this one didn't have. So if this one adds up to 6, I think you can guess that this one's going to add up to 3. Okay? Why? Because it's going to be 3 less than this one because it's missing the 3. This term right here doesn't have a 3 in the front. So, what am I getting at? Whether the series starts at 1 or 2 or 3 or 4, it really doesn't have any bearing on whether or not the series is going to converge or diverge. All it has an effect on is what does it converge to. So keep that in mind as we go through a lot of these series we're going to talk about. Is the index, where the index starts, does not affect whether or not the series converges or diverges. It's the terms themselves that affect that and how that pattern of terms develops. But it will affect what the series will converge to. So a geometric series will only converge to a over 1 minus r if that geometric series started at 0. If not, then we could still figure out what the series is going to converge to. We just got to figure out what we're missing from that a over 1 minus r. Let's say we were missing the first 2 terms or the first 3 terms. Well, we would figure out what the sum is if we had those terms, and then we would have to take all these off of it. All right. Let's look at this other example I have on here. Erase. Give me a second. Make some room here. All right. So you may hear in this video some background noise. It's because I'm sitting in my car on my driveway making this video, and it is currently pouring really hard. So just gotta bear with me. Anyway, back to this problem. So let's look at this one. This one is also a geometric series. If you look, this is in the form of the sum of n equals 0 to infinity of a r to the n. A, in this example, you could say there's a 1 out in front here. And this 3 halves is my r. So this is a geometric series. R is 3 halves, because it's r to the n, 3 halves to the n. The absolute value of r is greater than 1. Therefore, the series diverges. Why? Because that's what this theorem told us. If the absolute value of r is greater than or equal to 1, the series will diverge. Alright, so I figured I'd give you a little picture of, yeah, see, I'm sitting in my car. Yes, it's pouring outside. Alright, so let's get back to work. So, the question that I want to ask is, why? Why does a geometric series converge or diverge based off of R? Well, really, it's because of the partial sums concept. So let's take a look at a geometric series real quick. So we have this geometric series, n equals 0 to infinity, of AR to the n, which is A plus AR plus AR squared plus AR cubed, AR to the fourth, etc. Okay? And let's look at some partial sums. So let's look at, say, I don't know, the first partial sum, which would be A. Let's look more specifically at the nth partial sum, which would be A plus AR plus AR squared plus AR cubed plus AR to the fourth. Keep going all the way up to AR to the n minus 1. Okay? N minus 1, because if you look at the first term itself, right? This is AR to the 0, but it's the first term. So if I plug 1 in, I have to have 0 here, so it's always 1 less than this. So that's okay. So then what I'm going to do is I'm going to take this nth partial sum, and I'm not going to take the limit of it right now, because it's not really the formula I have generated for this thing. So what I'm going to do instead is I'm going to multiply this nth partial sum by r. So that would give me AR plus AR squared. Every single one of these terms has to be multiplied by r. So the power is going to bump up by 1 on every single one of these, all the way down till this last one's going to now be AR to the n. Okay? Then what I'm going to do is I'm going to say, let's look at S sub n minus R S sub n. Let's take this minus this. And if we do that, look what happens. This minus this, these will cancel, 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 this will cancel from whatever's before that. And I'll be left with this minus this. Then what I'm going to do is I'm going to factor out S sub n on this side and be left with 1 minus r. On this side, I'm going to factor out an a. I'm left with 1 minus r to the n. I'm going to divide this 1 minus r, and I get S sub n equals a times 1 minus r to the n over 1 minus r. Now, why did I do all this? Well, remember, what we're trying to do is come up with a formula for the nth partial sum. Now, I did it a fairly unorthodox way comparative to what we were doing in our previous examples, but ultimately, it doesn't matter how I get here. Do I have a formula for the nth partial sum? Yes, I just created a formula for the nth partial sum. So now if I want to find the limit as n goes to infinity of the formula or the function that represents the nth partial sum, I can do that. So it's the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r. Now remember, a and r are both constants. So to do this limit, what I could say is since a is a constant and r is, 1 minus r is a constant, that whole thing can be a constant multiple I can pull outside the limit, because none of that's affected by n. Then I really just have to take the limit as n goes to infinity of 1 minus r to the n. Now here's the thing, r to the n is an exponential function. Depending on what r is, that thing acts differently as n goes to infinity. You think about your exponential function. You have two exponential functions. One does this, one does this. Okay? This one is when your base is greater than 1. This one is where your base is less than 1. The base in this case being r. So this limit has two different answers. If r is greater than 1, then as n goes to infinity, the function itself is going to go to infinity. So this whole thing goes to infinity. And what does that mean? It means that the limit goes to infinity, the sequence diverges, and the series diverges. But if r is less than 1, and we're talking about absolute value in this case because the base of an exponential always has to be, we're talking about the base being positive. But anyway, let's go less than 1. As n goes to infinity, the exponential itself gets closer and closer to 0. So this thing goes to 0, and therefore this limit goes to 0, or this limit goes to 1 because you'd have 1 plus 0, and you have just this left over. So you would get, if r is less than 1, you would get a over 1 minus r as your answer, which is just a constant, and therefore it converges. Now we still haven't figured out what happens when it equals 1. When it equals 1, we would have to look at that type of function, and we can use some logarithms essentially to help us come up with that one. But without getting all the way into this proof right now, I'm just trying to give you an idea of where that theorem comes from. Equals 1 will also end up falling into this case, and this is exactly what the geometric series theorem just said. So why does a geometric series converge or diverge based off of r? This is why. All right, we have another theorem or test. We're going to call these things tests, theorems. It doesn't really matter. It's ways of determining whether or not a series converges or diverges. So right now we have two. We have the partial sum theorem or test. Okay, this is if we look at the sequence of partial sums, what happens to the sequence of partial sums tells us what happens to the series. Then we have very more specifically, if a series is a geometric series, if it's set up to have the properties of a geometric series, then we can determine if it converges or diverges based off of the ratio r. Then we're going to have this other one now that's going to be called the nth term test or nth term theorem. Okay, so it's based off of an if-then statement. Okay, now this if-then statement right here really isn't helpful at all in itself, but it is helpful in that it gives us this if-then statement. Now you got to understand if-then statements. There's a course you could take called Logic, which looks at different logical statements and their validity and their truth values based off of the pieces of the statement. So we have if something, let's say if P then Q. Okay, so if in this case a series converges, that's the P, then the limit as n goes to infinity base of n equals 0. That's the Q. And so what this says here is something that more or less should be thought of really as common sense. So if this particular series converges, then the terms of the series, which a sub n represents the terms of the series, have to be going to 0. They have to be getting smaller and smaller and smaller. If you add a series, say 1 plus 2 plus 3 plus 4 plus 5, those terms are not getting individually smaller, right? So your first instinct is, as I keep adding, what's going to happen to the sum? It's going to keep getting bigger and bigger and bigger. What this if-then statement is saying is if I look at a series, and we've already looked at a couple that converge, but let's say we look at the 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, etc. If this series converges, which we know it does, this converges. We know it already, which is why this if-then statement is not really that helpful, but I'll get into that in a second. If this converges, which it does, then the terms had to have been getting closer and closer and closer to 0. Okay? So that's what this if-then statement says. But the problem is the first part of the if-then statement is saying if the series converges. We don't know if any of these things are going to converge or not. We have no idea. We don't know that first part. So that's why this statement is kind of not very helpful right now. But if we do know that a particular series converges, what had to have happened was that the terms themselves had to get closer and closer to 0. Okay. Now there's some problems with if-then statements. Okay? Just because you say if a series converges, then the terms had to have gone to 0, doesn't necessarily mean you can then read it the other way. That if-then statement right here is not the same thing as saying if the limit as n goes to infinity of a sub n equals 0, then the sum of a sub n converges. That all I did was flip this and this around in the if-then statement. And if I do that, this and this do not mean the same thing. In fact, it can be shown that this is not true. If this is true, it can be shown that this is not necessarily true. Okay? Sometimes it is, sometimes it isn't, but not always. So if-then statements are tricky. If P then Q is not the same thing as if Q then P. Okay, they're not the same thing. But there is something that is equivalent to this statement, and it's something called the contrapositive. It says if I wanted to flip the roles of P and Q, I can do that as long as I negate both pieces. Now, negate means do the opposite. So the way you say negate with a symbol is that little tilde, that symbol right there. Then, you know, this would be, sorry, if Q, because I'm flipping their spaces, okay, I can negate them. Well, if I negate limit equals 0, that's not equals 0. Okay? If I negate converge, then that's diverge. Negate means the opposite. Okay? So if I wanted to flip this around so that this piece was here and this piece was here, and I want it to be equivalent to this original statement, at this point you can't see it because I've written over it so much. If I want it to be equivalent to this statement, I have to do the contrapositive, which is negate both of these pieces and then flip them around. All right. That's a lot of information there. You can get more into logical statements and if-then statements if you were to take, say, a class called logic or even discrete mathematics. You get into this type of stuff. It's very important when it comes to proof writing that your logical statements, you know, follow one another. So anyway, let's look at this one though. So if we look at this one right here, what is it saying? If the limit as n goes to infinity of a sub n doesn't equal 0, then the series will diverge. This is so much more helpful because it's telling us whether or not the series will diverge. We don't know that. It's going to tell us that if the terms don't go to 0, which that should also make sense to you as well, just from fairly, using common sense. It's this example I gave you a second ago, 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay. The terms themselves are not getting closer and closer to 0, but getting further away from 0, in fact. And because those terms are not getting closer and closer and closer to 0, they're getting bigger, which isn't necessarily a requirement, just not closer to 0. You clearly, as I keep adding, this thing is going to go to infinity. But it doesn't have to even be getting bigger. I could say, if I go 1 plus 1 plus 1 plus 1 plus 1, we already looked at that one. We saw that that one diverges too. It goes to infinity because the terms themselves are not getting smaller and going towards 0. They're staying the same. They're getting closer and closer to 1. In fact, they all are 1. So if the terms don't equal 0, then the series will diverge. Just because the terms do go to 0 doesn't mean it's going to converge, though. That's something you got to watch out for. You can't read more into an if-then statement than what it says. So this if-then statement right here, which is the nth term test for divergence, only says diverges. This says nothing about convergence. So when I'm looking at using the nth term test, I can never use the nth term test to determine convergence. The nth term test only tells me about divergence. So when I look at these examples, if this happens, I can say the series diverges. Otherwise, I can't say anything about the series. So let's look at the terms of the series here. The terms of the series are all 2 to the n. If I look at the limit as n goes to infinity of 2 to the n, what do I get? Well, as n gets bigger and bigger and bigger, that gets bigger. That thing goes to infinity, which is not 0. And as long as the limit as n goes to infinity of a sub n is not 0, then the series diverges by nth term test. Let's look at this one. These are the terms of the series. If I did the limit as n goes to infinity of n factorial over 2n factorial plus 1, without doing a whole lot of work, you could see that I have a factorial on the top and a factorial on the bottom. We talked about numerator and denominator functions, one growing faster than the other or at the same rate. These are the same function. So you should probably realize that this limit as n goes to infinity gets closer and closer to a half. Well, that's not 0. So the terms themselves are getting closer and closer and closer to a half. Well, as long as it's not 0, then the series diverges by nth term test. Okay. All right, let's go one more. Here's this one we've looked at already and we weren't able to do. We said to be continued. So let's take the limit as n goes to infinity of 1 over n. That's the terms, right? Take the limit as n goes to infinity of all the terms individually, which is 1 over n. What do we get? As n goes to infinity, the denominator goes to infinity, so the whole thing goes to 0. Well, there's the problem. If the terms do go to 0, we don't know anything. The terms going to 0 does not guarantee convergence. Not going to 0 guarantees divergence, but going to 0 does not guarantee convergence. So this one, nth term does not apply. So we still don't know whether or not this thing converges or diverges. Still to be determined. Okay. The thing with terms going to 0, right? This series here, all the terms are getting smaller and smaller and smaller. Let's see here. I'm going to write, this is going to be a mess, but let's look at this series here. It's 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6 plus etc. That's what this series looks like. The terms themselves are getting smaller. The terms themselves are going to 0. But that doesn't mean that this sum as a whole is finite. What would make this sum finite is determined by how fast these terms are going to 0. The faster these terms go to 0, the more likely this series is to converge. But just going to 0 isn't enough. Okay? Going to 0, if the terms go to 0, the series still could diverge. If they don't go to 0, it guarantees that they're going to diverge. But going to 0, it could converge or diverge. It's about how quickly do these go to 0. And I'm telling you, this one, they don't go to 0 fast enough. This one's going to end up diverging. But we haven't seen why yet. That's why it's still to be continued, to be determined. All right, there's a couple of properties we can do with infinite series, not a whole lot. Um, if we're trying to work with a series and maybe simplify a couple of series or so on, there's a couple of things we can do. We don't really do a whole lot of this because there's not a lot to do. But what it says is a couple of things. One, if we have two series that definitely converge, and the key is we have two series that we already know converge. This series converges and this series converges. Okay? A couple of things need to happen here. This one has to start and this one has to start at the same spot. So let's say they both start at 0 and go to infinity. If they don't start at the same spot, these two are a little bit harder to show. Okay, well, here I have them showing starting at 1. So let's just say these both start at 1. Okay, but they have to start at the same place. So if I have two series, A sub n and B sub n, they both converge. This one converges to A, this one converges to B. And let's let C be some other random number. We have first this first property, which is the constant multiple rule. So if I know that the sum of A sub n converges, then C times A sub n should just be C times whatever A sub n converged to, so C times A. So what it says is you can take a constant multiple, pull it outside a series, find the sum of the series without the constant multiple, then multiply it back in. All right. Then you have these two, which is the sum and the difference rule. So what this is saying is if I know that the sum of A sub n converges and I wanted to add the sum of B sub n to that, and that also converges, since this converges to A and this converges to B, then the sum of this whole thing should be A plus B. Now, that's the basic gist of it. If I wanted to put this together as one series like this is, they would have to start at the same spot for me to be able to do that. But nonetheless, the concept is if this one converges to A and this one converges to B, then the sum of the two of them should converge to A plus B. And the same thing should go for the difference. So there's not a whole lot going on here. Like I said, we're not going to do this a whole lot. But there's very few properties we have when it comes to infinite series and infinite sum. You notice there's no like product rule, quotient rule, none of that stuff. Like what can you do with the product of two series or the sum of two, or the quotient of two series. So let's just say these are a couple of properties, take note of them, and we'll move on from there.